The lightning current may have traveled through the metal vent and into the building's electrical system. Lightning can create conductive paths in the air, jumping across small gaps. It may have created an arc to the nearest electrical wiring or components. The intense electromagnetic field generated by the lightning strike may have induced currents in nearby electrical conductors, even if there was no direct contact. The sudden voltage spike caused by the lightning strike can damage sensitive electronic equipment, such as TV, computers, and phones. The induced currents or sparks from the arc may have caused damage to electrical components within ground fault circuit interrupter receptacles. The underground service line connecting the two houses may have acted as a conductor for the lightning current. If the two houses share a common grounding system, the lightning current could have traveled through the ground wire and into the neighbor's electrical system. If the house or nearby structures were not equipped with lightning rods, the lightning may have entered the building through an unintended path. There could have been concealed wires or plumbing in the attic that provided a path for the lightning current. Moist wood can conduct electricity, providing a possible path for the lightning current to reach the ground. The intensity and duration of the lightning strike can influence the amount of damage caused. The closer the equipment was to the point of impact, the more likely it was to be affected. The absence of surge protection devices may have exacerbated the damage caused by the lightning strike. When lightning strikes a building, its immense energy seeks the path of least resistance to the ground. This path isn't always obvious, and several factors can influence how the current flows and what equipment is affected. Firstly, metallic paths provide a direct route for lightning current. In this case, the metal vent in the attic likely acted as an initial point of contact. The current then could have traveled through the vent and into the building's electrical system, following wiring, metal conduit, or even plumbing. Secondly, air gaps can be breached by lightning. Lightning can create conductive paths in the air, effectively jumping across small gaps. This phenomenon, known as arcing, can occur between the metal vent and nearby electrical wiring or components, even if they are not in direct contact. Thirdly, induction plays a significant role. The intense electromagnetic field generated by a lightning strike can induce currents in nearby electrical conductors. This means that even if wiring is not directly hit by lightning, the electromagnetic field can create a current within the wires, potentially damaging connected equipment. Surge damage is a common consequence of lightning strikes. The sudden voltage spike caused by lightning can overwhelm and damage sensitive electronic equipment such as televisions, computers, and telephones. This surge can travel through the electrical system, affecting devices plugged into outlets. Electrical arcing can also damage components. The induced currents or sparks from the arc caused by lightning can damage electrical components within ground fault circuit interrupter receptacles. This is because the surge can overwhelm the delicate circuitry of the ground fault circuit interrupter, causing it to fail. Underground service lines connecting houses can act as conductors. If the house and the neighbor's house are connected by an underground service line, this line can act as a conduit for the lightning current to travel between the two properties. A common grounding system can also transmit current. If the two houses share a common grounding system, the lightning current could have traveled through the ground wire and into the neighbor's electrical system. This can happen if the grounding electrodes of the two houses are connected, allowing current to flow between them. The absence of lightning rods is a contributing factor. If the house or nearby structures are not equipped with lightning rods, the lightning may enter the building through an unintended path. Lightning rods provide a designated path for lightning to travel to the ground, reducing the likelihood of damage to the structure and its electrical system. Concealed wires or plumbing can also conduct electricity. There could have been concealed wires or plumbing in the attic that provided a path for the lightning current. Even if these are not part of the intended electrical system, they can still conduct current and cause damage. Moisture can also play a role. Moist wood can conduct electricity, providing a possible path for the lightning current to reach the ground. This is especially true in humid environments or if there are leaks in the roof. The intensity and duration of the lightning strike can influence the amount of damage caused. A more intense or longer-lasting strike will generally cause more damage. Proximity to the impact point is another factor. The closer the equipment was to the point of impact, the more likely it was to be affected. This is because the intensity of the electromagnetic field and the surge voltage are greatest near the point of impact. The absence of surge protection devices may have exacerbated the damage caused by the lightning strike. Surge protectors can help to divert excess voltage away from sensitive electronic equipment, reducing the risk of damage. Consider a scenario where lightning strikes the metal vent and the roof. The surge of electricity then follows several paths. Firstly, some current travels down the metal vent into the attic space. Secondly, the electromagnetic pulse induces currents in nearby wires even if they are insulated. Thirdly, a portion of the current travels through the home's electrical wiring. Let's explore what happens in each of these situations. As current travels down the vent, it jumps to the electrical wiring via arcing. This electrical arcing creates a very high temperature and a voltage surge that damages the nearby 8 to 10 foot electrical home runs, not through direct contact, but through the creation of a strong electromagnetic field. The transient voltage makes its way into the electrical panel, passing the voltage onto any branch circuit. Another path is that the lightning travels through the electrical ground wiring. This scenario causes issues because the voltage passes through the ground wire into other appliances plugged into the ground. The neighbor's house experiences electrical damage because the ground is connected through the grounding electrode conductor, which is required by the National Electrical Code Section 250.50. This passes through the service lateral underground. In addition to these paths, consider the role of moisture. If the wood in the attic is damp, it becomes more conductive. This creates an additional pathway for the electricity to spread, increasing the area affected by the lightning strike. The absence of surge protection plays a crucial role in the extent of the damage. Without surge protectors, sensitive electronic devices are left vulnerable. These devices, such as televisions, computers, and ground fault circuit interrupter receptacles, are easily damaged by voltage spikes. Therefore, the combination of these factors, metallic paths, air gaps, induction, moisture, lack of surge protection, and the interconnection of grounding systems can explain how a lightning strike can cause widespread damage to both the house that was struck and the neighboring house. In this emergency, the fact that the fire was contained to a small area does not mean the electrical damage was similarly limited. Lightning's energy can travel far and wide through various paths, affecting equipment and systems well beyond the immediate vicinity of the strike. To mitigate future risks, it is important to consider installing lightning rods, surge protection devices, and ensuring proper grounding of electrical systems. Lightning rods provide a direct path for lightning to travel to the ground, reducing the likelihood of damage to the structure and its electrical system. Surge protection devices can help to divert excess voltage away from sensitive electronic equipment, reducing the risk of damage. Proper grounding ensures that electrical systems are safely connected to the earth, providing a path for fault currents to flow and helping to protect against electrical shock. The National Electrical Code, or NEC, provides guidance on grounding and bonding requirements for electrical systems. Section 250 covers grounding and bonding, including requirements for grounding electrodes, grounding electrode conductors, and equipment grounding conductors. Section 280 addresses surge protection devices, including requirements for installation and performance. Section 800 covers communication systems, including requirements for grounding and bonding of telephone and data equipment. In addition to the NEC, other standards and guidelines may be applicable depending on the specific location and type of electrical system. These may include local building codes, utility company requirements, and industry best practices. Regular inspection and maintenance of electrical systems can help to identify and address potential hazards, such as damaged wiring, loose connections, and corroded grounding electrodes. It is also important to ensure that surge protection devices are properly installed and functioning correctly. Consider a scenario where the house is equipped with lightning rods. The lightning rod would provide a low resistance path for the lightning current to flow to ground, diverting it away from the building's electrical system. In this case, the damage to the electrical system would likely be significantly reduced. Similarly, if the house is equipped with surge protection devices, these devices would help to protect sensitive electronic equipment from voltage spikes. The surge protectors would divert excess voltage away from the equipment, preventing damage. In contrast, if the house is not equipped with lightning rods or surge protection devices, the lightning current will likely find its way into the building's electrical system, causing widespread damage. This is because the electrical system provides a relatively low resistance path to ground compared to other paths. Consider the grounding system per NEC 250.50, which requires all grounding electrodes to be bonded together, creating one common grounding electrode system. As previously mentioned, the ground fault circuit interrupter receptacles were damaged. Ground fault circuit interrupter receptacles are designed to protect people from electrical shock by detecting ground faults. When a ground fault is detected, the ground fault circuit interrupter receptacle quickly trips, interrupting the flow of electricity and preventing a shock. In this case, the lightning strike likely caused a voltage surge that damaged the ground fault circuit interrupter receptacles, rendering them inoperable. This can happen because the surge overwhelms the delicate circuitry of the ground fault circuit interrupter, causing it to fail. To prevent this type of damage, it is important to use surge protection devices on circuits that supply ground fault circuit interrupter receptacles. Surge protection devices can help to divert excess voltage away from the ground fault circuit interrupter receptacles, protecting them from damage. It is also important to ensure that the ground fault circuit interrupter receptacles are properly grounded. Proper grounding ensures that electrical systems are safely connected to the earth, providing a path for fault currents to flow and helping to protect against electrical shock. The National Electrical Code provides guidance on grounding and bonding requirements for electrical systems. Section 250 covers grounding and bonding, including requirements for grounding electrodes, grounding electrode conductors, and equipment grounding conductors. In addition to the NEC, other standards and guidelines may be applicable depending on the specific location and type of electrical system. These may include local building codes, utility company requirements, and industry best practices. Regular inspection and maintenance of electrical systems can help to identify and address potential hazards, such as damaged wiring, loose connections, and corroded grounding electrodes. It is also important to ensure that surge protection devices are properly installed and functioning correctly. When assessing damage from a lightning strike, it's crucial to consider all possible paths the current might have taken. This includes not only the obvious routes through wiring and metallic components, but also less apparent pathways like air gaps, induction fields, and shared grounding systems. This comprehensive approach is essential for understanding the full extent of the damage and implementing effective preventative measures. In a given scenario, several factors converge to cause the widespread damage. The metal vent provided an entry point, the lack of surge protection left devices vulnerable, and the interconnected grounding systems allowed the current to spread to the neighbor's house. Understanding these mechanisms is essential for preventing similar incidents in the future. This requires a multifaceted approach, including installing lightning rods, implementing comprehensive surge protection, and ensuring proper grounding and bonding of electrical systems. In this specific case, it is important to consult with a qualified electrician to assess the damage and determine the best course of action. The electrician can inspect the electrical system, identify any damaged components, and recommend appropriate repairs or replacements. The electrician can also assess the grounding system and ensure that it is properly installed and functioning correctly. In addition, the electrician can recommend surge protection devices and lightning rods to help protect the house and its electrical system from future lightning strikes. Finally, it is important to document the damage and file a claim with the insurance company. The insurance company may require an inspection of the damage by a qualified electrician or engineer. The insurance company may also require documentation of the damage, such as photographs and receipts. By taking these steps, it is possible to minimize the damage from a lightning strike and protect the house and its electrical system from future damage. In summary, a lightning strike can cause widespread damage to electrical systems, even if the strike is not direct. This is because lightning can travel through various paths, including metallic components, air gaps, induction fields, and shared grounding systems. To prevent this type of damage, it is important to install lightning rods, implement comprehensive surge protection, and ensure proper grounding and bonding of electrical systems. It is also important to consult with a qualified electrician to assess the damage and determine the best course of action. By taking these steps, it is possible to minimize the damage from a lightning strike and protect the house and its electrical system from future damage.